swimming pool with one of those trucks or the shovel that he had outside or the bobcat when he rented it. He handed me a spoon, and so I took it seriously and went out and started digging. But did you know that you can find some pretty cool stuff when you're digging in the dirt? Especially when you're digging with a spoon, and small hands can hold it. Sometimes mathematics research can feel like you're trying to find the biggest bulldozer you can. And then there's another end of mathematics where you're trying to see how small you can make your spoon. And that's the direction that this presentation is going to take. How can we try to dig a swimming pool or do something amazing with a spoon? Or with a really low-tech, very accessible tool? Things that are going to make sense to us and resonate with us. One reason why we sometimes try to do this is when we look at this long conversation with humanity, like the beginning of math, the end of math, there was a time when they discovered irrational numbers, the Pythagoreans, right, Hypasus. And from the writings of Plato, we have little hints that maybe it was already done. There were these fictional stories by Plato. One of them said that they had figured it out for the square roots of 3 through 17. And so many people have conjectured that it was probably because of this. It's called the Spiral of Theodorus. That was the fictional character that Plato wrote about. And the reason why they think that is when you go all the way around, you're like, oh, then they ran out of room and they didn't think to take it any further. Well, it's always bothered me that the square root of 2 is right there. Why didn't they include that too? Why didn't Plato mention 2 to 17? Not 3 to 17. Why not 2 to 17? So I have a suspicion that maybe there's something about geometry that could work with this as well. And maybe this was just a conjecture. I don't know. I mean, it's all kind of a guess. I'm trying to engage in this really long conversation. So one reason you might say, I want to try to do this using very simple tools is because this was thousands of years ago. They didn't know too much. They had Euclid elements. You want to use the spoon to try to see, well, what could they have done? Especially because Plato said in this fictional work with Theodorus that it was taught to a child or a youth in one lesson. So that's a small spoon. So I have some ideas, and I've seen some ideas from others that might inform that, and that's going to be also one of the reasons why I hope you enjoy this mathematics. So maybe this spiral wasn't the tool. Maybe it was something else. And that's what I'm going to try to present to you today that I've just started working on. My spoon. The carpet's theorem is very simple that a child can understand, but it takes a moment to think it through. And if I were talking to a child and I said, imagine that we're in a room with no carpet, and then also we have its floor covered with carpet. So step 1, no carpet. Then we're going to cover it with carpet. And it's covered completely perfectly, like 2 pieces of carpet. Say we got a triangular carpet and then this other shaped carpet that's also quadrilateral, and they happen to perfectly make the area of the room. Then, next part of the story to this child, if you were teaching this as a lesson, is say, let's say we pick up the triangular one, or either of them, and just move it. If you move it and put it back down, it's going to partially overlap, like it's going to, right? And then, when it overlaps, it makes 4 different regions. You could show the student those 4 different regions that are created. And then in this picture, you can see, this is like a proof without words, maybe tradition, because you can almost see what's happening instead of having a lot of words in the proof. You could show the child, it's low-hanging fruit, that this shape ought to be the same as this shape. Why? Because I moved that carpet that was triangular shaped. So they're the same shape. They have the same area. It's like an equation with symbols. Could you solve that equation with symbols? What could you do to both sides? What would you think is coming next?
write a tiny triangle?
You could kind of do something to both sides. Maybe subtraction might be a good way to think about it, but when you notice that this is the same on both sides, just like in algebra that you've been trained to do, like, oh, that must mean that that must mean that those other parts are the same size. Seems logical? Yeah. And then this is the Carpets theorem. It's not named for Professor Carpets, it's actually about carpets. The Carpets theorem is that the uncarpeted area is going to equal the doubly carpeted area. And I think maybe this might have been the spoon that was taught or handed to that youngster and said, see if you could prove that the square root of 2 is irrational using this. So you've got the Carpets theorem as your spoon. Okay? Somebody's done this before, but I'm going to change what he did. This is Stanley Tenenbaum. He was a logician. He did this in the 50s, his proof, called the Tenenbaum proof, for lack of a better term. And he was a student of John H. Conway. And then in the 1990s, John H. Conway showed this group when he was giving a talk. And since then, it's been kind of famous. It's because of its simplicity and its beauty. I'm going to show it to you, and then I'll show you why I changed it. So he said, using the Carpets theorem, imagine you have a square-shaped room, and 2 carpets that are also squares. He said, not only that, this is special. It's a proof by contradiction is coming. He said, let's suppose that this has an integer side length. Those have integer side lengths. Could happen. Oh yeah, and another thing. Suppose that the area of the carpets is exactly the area of the room. Kind of like the first example I showed you. Just suppose. Suspend your disbelief. Could happen. Put the carpets in the room. Maybe one in each corner. That's a nice idea. We put one of them, I did it in a gray, I put one of them up against this vertex, and one of them where they share that vertex. And then it would create uncarpeted areas and a doubly carpeted area. They're all squares. And if the uncarpeted areas equal the doubly carpeted areas, by the Carpets theorem, then this is a counterexample to any assumption we make that there's a smallest one. So there's that well-ordering axiom. If you have something like positive integers, there's a smallest one, right? So if you said, let's just assume that the original squares are the smallest possible case, we have a contradiction because we just found 2 squares that equal another square. You can show that they're integers because, if this is an integer, which it is by his assumption, and this is an integer, which it is by assumption, then this would be an integer as well. And so that would be a counterexample to his original assumption that it was the smallest case. So this was, some people have guessed that it might be related to how the square root of 2 or the square root of 3 or any of those numbers, I guess the square roots of 3 through 17, those non-square numbers by hypasis, might have been how Plato was referring to what was learned. But I changed it because these are squares, and I have a feeling, and this is the square root of 2. Remember how hypasis started with the square root of 3? It's like, what if there was something more geometric? So I decided to make up a word, and I'm going to let you kind of make friends with this. It wasn't my abstract, but still, I'll read it and show you some examples. In Euclidean geometry, I decided to use the word nice. It's a nice drawn if you actually have integer side lengths and it's regular. So like this one's nice and that one's nice. Because they have integer side lengths and they're regular. Got it? And then grational, or grationality. In order to set up these types of proofs that are similar to what Tenenbaum did, I wanted to use the word Grational because I want to hold it in geometry, where a 3-year-old can think about shapes, or some kind of youth can think about shapes. Not number theory, it's in the background. That's the bulldozer that my dad was using. I want to hold back and think about shapes. So, if an integer is Grational, then there are nicegons, such that the area equals the area, or sorry, its area equals the sum of areas of incongruent nicegons. So, for example, this is a 4-gon, it's a square, and I have area 4, that's the big one. The little ones have area 1 each, and that 1 plus 1 plus 1 plus 1 is 4. Hopefully I said that the right number of times. So this means the number 4 is Grational. So this is what I did with squares. And I didn't do 2 because I can't make a 2-gon. So in my geometric interpretation of rationality, which is Grationality, I'm not looking at 2 because that doesn't make sense to have a 2-gon. It does make sense to have a 3-gon. So that's why I'm thinking maybe this idea could help us think differently about what Hypasus did. Yes. 3 is not Grational. Grational. Here's my proof. Let's say we have a triangular carpet. That's a 3-gon. So I'm starting with the first polygon that I can. A regular equilateral triangle that is nice. There must exist then 3 nicegons, or 3 nice 3-gons. They're equilateral triangles. When you add up those areas of the carpets, you get the area of the room. I'm going to try to prove it kind of like Conway did with the other one, except with triangles. So I'm going to first suppose not. Let's say it is rational. And then let's see if we can get a contradiction. They're all nice by assumption. And I'll assume, well-ordering principle, that this is the smallest one. Let's see if we can get a contradiction. Then I'll put the carpets in the room. There's no prescription of how, but I chose to try to do something similar to what Tenenbaum did and put one in every corner. I've toyed with the idea of trying different arrangements, and you should too as you play with this on your way home, you know. And at first, as a good proof, when you draw a picture, you have to kind of show yourself that you're allowed to draw a picture. So I made the little argument in my paper that, well, it would look like this because A is less than 2B, creating an overlap here. Whoops. Creating an overlap here. And A is less than 2B can be shown. Every little argument I made in the paper, I tried to make my spoon as small as I could. I didn't use algebra or analysis. I used pictures. And with tiling, triangles, equilateral triangles, tiles together so well, which would also be low-hanging fruit to understand, I can show that even something like that A is less than 2B, because, well, by my assumption, A is 3B, capital A is 3B, but then if I tile together 4 B's, I would get something that's 2B, and so 3 is less than 4. That's my small spoon. 3 is less than 4, so therefore this must be true, because I can see that with tiling. And then, is that side length an integer? Yes. 2B minus A is an integer. And that then can lead us to get an expression for, so I'm looking now, and you probably have already figured this out. Looking at the overlap areas, there are 3 of them, 1, 2, 3. And I'm looking at what size are they, because potentially that could be a counterexample. 1, 2, 3 triangular regions, those are the doubly carpeted areas, they have to equal the non-carpeted area. If they do, and if they're nice, then we have a counterexample. So I just need to see if they're nice. So I figured out that that one was 2A minus 3B. As long as that's positive, that sounds like an integer. To show it's positive, the little girl with the spoon would have to know, is 2A bigger than 3B? She could figure that out also with tiling. that 2A is bigger than 3D. So I was really rigorously showing that, yes, I know these things, and I know them for basic reasons, right? Very observable, direct ways. So those 4 triangles are nice, and by the carpet theorem, the sum of the smaller triangles equals the sum of the larger triangles. So this is a contradiction, a counterexample. Thus, 3 is not rational. You get the idea? We're going to do 5, we're going to do 6, and then I'll show you 9 n squared. So we have some theorems, and it gets more interesting, but this is the idea. Proof by descent like this is very hard to generalize, notoriously difficult to generalize. So I was looking for patterns, and I haven't been all the way to 17, which is hypothetically maybe a hint of what happens when I get there, but I've done some of them.